The first talk is given by David Binks on status and scope of ESA's ISRU demonstration mission. And John, if you want to, David, sorry, if you want to share your screen. And yeah, take it away.
So good morning, everybody. It's very much appreciate the invitation to speak. And this talk's going to go through some of the give the scope and the status of the ISRU demonstration mission. So it's just a short overview of the scope of our mission here at ESA, and of course it's somehow intended to be a warm-up for the more detailed technical talk of John Vrubeskis coming up after this. So basically, I mean, as we know, that explorers have always utilized resources when they've gone to new places. It's simply impractical to carry all your supplies. I mean, to some extent, even getting a bucket and getting some water from a stream when you're exploring is somehow a form of ISRU. But of course, this has not always been the case in space exploration. Now, since the moon is now a key destination for the human robotic exploration directorate in ESA, we need an affordable and hence sustainable human presence on the moon would require utilization of resources, so the so-called paradigm living off the land, as our director has often mentioned. I mean, to implement ISRU, I mean, it's not easier said than done. We taken a stepwise approach generally. So the idea is that we want to prospect to understand abundances and distributions and accessibility of any raw materials or which the resources that could be there that could be extracted. And then the next step is to demonstrate this technical feasibility of extracting these resources from a given raw material. And then finally is to produce, so to extract the resources from a local feedstock via an end-to-end demonstration to a fully scalable pilot plant. So to use the resources in a practical way, oxygen for astronauts, metals for construction, and so on, as part of an enabling element of a mission. Now, with recent research into reduction techniques, which is the term used for removing oxygen from a metal oxide, it could be foreseen that astronauts carry their own sort of version of this water bucket. In this case, it's a piece of hardware which converts the lunar material and planetary material into the oxygen and the metal. It's no mean feat, so therefore we have to prepare the technology and understand what exactly happens when we attempt to do this conversion. So we've tried to take into the factors on the screen. So the programmatic boundaries that we have from our member states, the lunar properties themselves, the impact of the processes on the engineering solution, preliminary sizing cases, and also the mission constraints. I mean, how do we visit the surface with our demonstrator? I mean, an initial assertion that we've had from the very early stages a few years ago was that this demonstration to be something which is of a visible scale, repeatable, and most importantly, representative of a future scale system. So this is a slide that some people may have seen before. It's an old one, but I think not to assume, as has been mentioned, a broad audience. I thought I'd mention just to recall some of the key parts of an end-to-end subsystem system of ISRU. So you can see on the chart that there's elements of excavation, so gathering the material, and elements of transfer and processing. This is the part where you would enrich to a specific mineral, if that's what you're looking for. This is the mineralogical beneficiation, and then there's the physical beneficiation. This is to put the material in a form which can be accepted by the reaction plant, which you see here in the right hand side of the screen. So in the reaction plants, we could assume a number of chemical processes, from carbothermal, from molten salt electrolysis, from molten oxide electrolysis, and so on. I won't go into the details of this. I've saved some of more of these details for John in the following presentation. And there's very, very much literature on the subject, so I encourage everyone to read into it. So I never found it very interesting and how these things work. But we need to consider, as we do not have infinite mass budget and power, the essentials to demonstrate. So basically, in a nutshell, we wanted to basically show in this presentation some of the stuff we've done in the past and where we are now. So for past work, I mean, we started with a knowledge gain basically. So we want to really find out what we could realistically do and what we could afford and what does it take. At the very beginning, we kind of said, well, let's make a bottle of water. But this has evolved through steps into tens of grams of oxygen through the literature research, experimentation, the system analysis, and the payloads, coming a bit more heavier and not sufficiently efficient. So you can see in the top left, we have the experiment which is done in the ESA lab by my colleagues Alexander, Maurice, and Beth Lomax of reducing lunar material. So this is a simulant on the left-hand side of the top left picture, and on the right-hand side of the top left picture is the metal tailings after the oxygen has been removed. And then the picture you see of the experimental setup from Beth's experiments there. And also we have done work in ESA's concurrent design facility in ESTEC, where we've analysed the system elements and the engineering designs, all different options. And Vanig is an example of one of the sort of the simple drawings we made for a robotic arm to understand its sizing case. So basically trying to figure out what could we want. And then, of course, we got to see if what we want is feasible. So we went into a phase A study where we traded off the processes, we traded off the various payloads against available flight opportunities. We generated a huge number of options and saw solutions to our first set of preliminary requirements. We evaluated these solutions and we modified these ready for preliminary definition. So going into phase B1, we had an idea of what we could get, bearing in mind the programmatic constraints. So we defined requirements for the phase B1. So going into the phase B1, we have now a number of high-level objectives to present. Now this slide may have been the next presentation, but I leave it to John to have his take on these objectives. So we want to look really at the excavation, so extracting the regolith from the surface and its handling and its transport of the material to a reactor. This is particularly important for reliability of future systems and preparing the technology and preparing the feedstock for loading and unloading. Now, this loading and unloading we consider to be the most important part of the system from an engineering perspective. Another really important part of the mission was the reduction of the regolith itself and what happens. So life expectancy of the system, its wear and tear, the upscaling issues to the use cases in the pilot plant, contamination issues, losses, and most importantly, the performance assessment and the experimentation involved in the process. We also want to do this operation in its relevant environment, so have a real dust environment, a real thermal environment, and also all the radiation effects also. Ultimately, an operational capability and a proof of capability before we take the next steps into larger investments in the use cases. So in the end, after we say all this preparation work, we ended with a production tie at around 50 to 100 grams. Now this was set, so we forced the idea of multiple batches because you could not do a single 100-gram batch in the landers we have available. Excuse me, because simply requires a fixed amount of energy to do any reduction reaction, and this is a energy per product mass, a metric like this. So hence at lower powers we reach a limit on the available energy and the available time we have on the surface. To keep the mission simple, we wanted to simply be in the lunar day. So we're always investigating, or currently, of course, how we can do more experimental runs beyond the 3 to 5 batches you see on the slides, but there needs to be a compromise between technology and science. I mean, the final point here is that we don't really somehow know the best way to do something, and you try and do it in a real scenario. So one example that I have used in the past is the Sojourner rover from Mars Pathfinder. This was preparation for the rovers now being used. So building the flying Sojourner was a key step in gaining the capability for something more ambitious a bit later. So I skip over these very, very fast. So the approach for phase B1 was the challenge, where we had four candidates that we selected in the normal tender evaluation on the ESA side, and we asked them to further develop their concepts. These concepts selected on the basis of requirements, compliance, how to handle mission constraints, and the vagueness of our interface requirements, because that's the reality of having multiple landers available and not being so certain about what the flight opportunity will be at this point. And of course, a risk assessment, so key factors such as the mass growth, the foreseen implementation schedule, the technology readiness of the concepts. So we try to take all these into account and and Thales UK, along with the consortium you see on the slide, came from the industry. So this is the current schedule. We are in the beginning of the phase B1, and we're going to very soon try to start technology development based on this system design in the areas of excavation, sample handling, preforming, the reactor itself, and the instruments. So very much quickly to conclude and somehow hand the baton to our prime contractor now. The goal is to develop a system which proves our ability to load, reduce, measure, and unload in the development environment and repeat, and then provide experimental data and measure performance to optimize ground development and generate know-how. And I'll point you to the web story that was released by ISRU some months ago now. It gives some good links to some of the more detail on the more of the experiments that have been done at ISRU in-house, and some more links there to ISRU's current design facility. So I stopped there.